The speed of light is not just fast, it is the fastest anything can go in our universe. At 299,792,458 meters per second, it represents the ultimate cosmic speed limit. This incredible velocity is built into the very fabric of physics itself, shaping how time flows, how space curves, and how cause and effect work throughout all of reality. But what would happen if we could rewrite this fundamental rule? Imagine for a moment that this seemingly unbreakable constant was not constant at all. Picture a universe where light, and with it all information, energy, and matter, could move instantly from one place to another, anywhere in the cosmos, in absolutely zero time. What if there was no speed limit whatsoever governing the movement of anything in existence? The answer to this mind-bending question would change absolutely everything we know about reality, including the very structure and behavior of the universe itself. Without this cosmic speed limit acting as a universal brake, the rules that govern stars, planets, galaxies, black holes, and even the flow of time itself would be completely and utterly rewritten from the ground up. Our entire understanding of physics would crumble like a house of cards, and then rebuild into something completely alien and unrecognizable. The night sky above us would transform into something beyond our wildest imagination. Space exploration and interstellar travel would become trivially easy, yet dangerous paradoxes would simultaneously threaten the very foundation of cause and effect relationships. This is not merely a simple mathematical change to one number buried deep in physics equations. This represents a complete and total reimagining of how reality works at its most fundamental and basic level. The speed of light does far more than just set a cosmic speed limit. It connects space and time into a unified fabric, creates the orderly flow of history as we know it, and prevents the universe from collapsing into complete logical chaos and contradiction. Remove this critical limit entirely, and we step boldly into a bizarre cosmos where everything happens simultaneously at once, where astronomical distance becomes completely meaningless, where the past and future blur together, and where the very concept of now takes on an entirely new and strange meaning that spans across the infinite expanse of space itself. In this altered reality, causality itself hangs by a thread, threatening to unravel the logical order that makes existence possible and comprehensible to thinking beings like ourselves. In our current universe, the speed of light in a perfect vacuum is exactly 299,792,458 meters per second. This number is not just another measurement that scientists have discovered through experimentation. It is actually defined to be exact by international agreement, serving as one of the fundamental constants that define our entire system of physics and measurement. But this speed represents far more than just how fast photons can travel through empty space. It is the ultimate speed limit for absolutely everything in existence, including information, gravity waves, electromagnetic radiation, and even the influence of cause and effect relationships themselves. When Albert Einstein formulated his theory of special relativity in 1905, he revealed that this speed limit creates some of the most mind-bending and counterintuitive effects in all of physics. As objects approach the speed of light, time begins to slow down relative to stationary observers through a phenomenon called time dilation. Simultaneously, the lengths of objects contract in the direction of their motion through length contraction. These are not optical illusions or measurement errors, but genuine physical transformations of space and time itself. The mathematics behind these effects becomes increasingly dramatic as velocities approach light speed. An object traveling at 90% of light speed experiences time passing at roughly half the normal rate compared to a stationary observer. At 99% of light speed, time slows to about 1/7 of its normal flow. At 99.9% of light speed, time crawls at roughly 1/22nd of its usual pace. As we push closer and closer to the speed of light itself, time dilation approaches infinity, meaning that reaching light speed would require infinite energy and result in time stopping completely. This speed limit also creates the foundation for understanding mass and energy relationships. Einstein's famous equation E equals mc squared emerges directly from the constraints imposed by light speed. The c in this equation is not just any velocity, it is specifically the speed of light, connecting mass and energy in the most fundamental way possible. This relationship explains how stars generate energy through nuclear fusion, how particle accelerators work, and why atomic bombs release such enormous amounts of destructive power from relatively small amounts of matter. The speed of light also determines how we experience causality itself. In our universe, cause must always precede effect, and this ordering is maintained by the light speed limit. Information about any event cannot travel faster than light, which means that the influence of any cause cannot reach distant locations instantaneously. This creates what physicists call light cones, which define the regions of space-time that can influence or be influenced by any given event. These light cones ensure that the universe maintains logical consistency and prevents paradoxes from occurring. Consider what happens when you flip a light switch in your room. The electrical signal travels through the wiring at roughly 60% of light speed, while the photons from the light bulb travel at full light speed to reach your eyes. Even these seemingly instantaneous events are actually governed by finite signal propagation times. On larger scales, this becomes even more apparent. When NASA sends commands to the Mars rover Perseverance, the radio signals must travel for anywhere from 4 to 24 minutes depending on the relative positions of Earth and Mars in their orbits. The speed of light also creates the phenomenon we observe as stellar parallax, which allows astronomers to measure distances to nearby stars. As Earth orbits around our star over the course of a year, we observe nearby stars shifting slightly against the background of more distant stars. This shift occurs because light from these stars takes a finite time to reach us, and our changing position in space means we are observing them from slightly different angles at different times of the year. In the realm of particle physics, the speed of light limit creates exotic behaviors in high-energy environments. When cosmic rays strike the upper atmosphere, they create showers of particles moving at significant fractions of light speed. These particles experience time dilation, allowing unstable particles like muons to survive much longer than they would at rest, enabling them to reach Earth's surface before decaying. Without this time dilation effect, many cosmic ray secondary particles would decay before reaching ground-level detectors. The speed of light also governs how electromagnetic fields propagate through space. When you move a magnet near a coil of wire, the changing magnetic field creates an electric field, but this change propagates outward as an electromagnetic wave at light speed. This principle underlies all radio communication, from AM and FM radio broadcasts to cell phone networks and Wi-Fi connections. The finite propagation time means that radio waves from distant galaxies have been traveling for millions or billions of years to reach our radio telescopes. Modern technology depends critically on accounting for light speed delays. Global Positioning System satellites must correct for both special and general relativistic effects related to their high velocities and positions in Earth's gravitational field. Without these corrections, GPS accuracy would degrade by several kilometers per day, making precise navigation impossible. The satellites experience time running slightly faster due to their altitude and slightly slower due to their orbital velocity, with the altitude effect dominating to create a net time advance of about 38 microseconds per day. In quantum mechanics, the speed of light creates fundamental limits on how quickly information can be transmitted, even through quantum entanglement phenomena. While quantum entangled particles can exhibit correlated behaviors instantaneously across arbitrary distances, no usable information can actually be transmitted faster than light through these correlations. This prevents quantum mechanics from violating causality and creating communication paradoxes. The speed of light also determines the structure of atoms themselves. Electrons in atoms move at velocities that are significant fractions of light speed, especially in heavy elements. The relativistic effects experienced by these fast-moving electrons influence atomic properties, chemical bonding, and even the colors of materials. For example, the golden color of metallic gold results partly from relativistic effects that modify the electronic structure of gold atoms. In astrophysics, the light speed limit creates observable consequences throughout the universe. When massive stars collapse into black holes, the formation process involves matter accelerating to significant fractions of light speed as it falls into the increasingly intense gravitational field. The energy released during these collapse events powers some of the most luminous phenomena in the universe, including gamma-ray bursts that can outshine entire galaxies for brief periods. The speed of light fundamentally shapes how we understand the universe's history and evolution. Every photon we observe from distant galaxies carries information about conditions that existed millions or billions of years ago. The Andromeda Galaxy, our nearest major galactic neighbor, appears to us as it existed 2.5 million years ago because that is how long its light has taken to reach us. The most distant galaxies, observable by the Hubble Space Telescope and James Webb Space Telescope, show us the universe as it appeared when it was less than 1 billion years old, providing crucial insights into cosmic evolution and star formation in the early universe. This finite light speed creates what cosmologists call the observable universe, which has a radius of approximately 46.5 billion light-years. Beyond this distance, light from more distant regions has not had sufficient time to reach us since the Big Bang occurred, roughly 13.8 billion years ago. The cosmic microwave background radiation that permeates all of space represents the oldest light we can observe, dating from approximately 3 billion years ago, 180,000 years after the Big Bang, when the universe first became transparent to photons. In particle accelerators like the Large Hadron Collider at CERN, scientists routinely accelerate protons to velocities exceeding 99.9999% of light speed. At these extreme velocities, the protons experience enormous time dilation and length contraction effects. A proton moving at 99.99999% of light speed would appear contracted by a factor of more than 70,000 to a stationary observer, while its internal processes would appear to slow down by the same factor. The energy required to accelerate particles approaches infinity as their velocity approaches light speed, which is why no particle with mass can ever reach or exceed this universal speed limit. The Large Hadron Collider consumes roughly the same amount of electrical power as a small city when operating at full capacity, yet it can only accelerate particles to within a tiny fraction of light speed. Even if we could somehow harness the entire energy output of our star for particle acceleration, we still could not accelerate a single proton to exactly light speed. The speed of light also governs the behavior of electromagnetic radiation across the entire spectrum. Radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays and gamma rays all travel at exactly the same velocity through vacuum, differing only in their frequencies and wavelengths. This universality means that when astronomers observe distant supernovae or gamma-ray bursts simultaneously across multiple wavelengths, all the different types of electromagnetic radiation arrive at Earth at the same time, despite having traveled for millions or billions of years through space. This constant velocity for all electromagnetic radiation enables techniques like radio interferometry, where multiple radio telescopes separated by thousands of kilometers can be synchronized to act as a single enormous telescope with unprecedented resolution. The Event Horizon Telescope, which captured the first direct image of a black hole's shadow in 2019, relied on precise timing synchronization between radio telescopes scattered across the globe, all accounting for the finite speed of light propagation between different observation sites. The speed of light creates fundamental limits on computation and information processing. Even in the most advanced computer processors, electrical signals cannot propagate faster than light through the microscopic circuits etched onto silicon chips. As processors become faster and smaller, engineers must increasingly account for light speed delays in their designs. In modern microprocessors operating at gigahertz frequencies, signals can only travel a few centimeters during a single clock cycle, creating challenges for processor architecture and layout. Optical fiber communication systems that carry internet traffic around the world also depend on the finite speed of light through glass. Light pulses carrying digital information travel through optical fibers at roughly 2/3 of the vacuum light speed due to the refractive index of the glass. This means that a signal traveling halfway around Earth through undersea optical cables experiences a minimum delay of roughly 67 milliseconds, which becomes noticeable in applications requiring real-time responsiveness, like high-frequency financial trading or online gaming. The speed of light also creates interesting effects in everyday materials and technologies. In metallic conductors, electrical signals typically propagate at speeds ranging from 30 to 90% of light speed, depending on the cable construction and surrounding materials. This finite propagation speed means that even electrical circuits in your smartphone or computer experience tiny but measurable signal delays that must be accounted for in high-speed digital design. Lightning strikes demonstrate another fascinating aspect of light-speed physics. When lightning occurs, we observe the electromagnetic pulse as visible light essentially instantaneously. But the associated thunder reaches us much later because sound waves travel at only about 343 meters per second through air at room temperature. This enormous speed difference between light and sound allows us to estimate lightning distance by counting the seconds between flash and thunder, then dividing by 3 to get the approximate distance in kilometers. Solar radiation provides another compelling example of light-speed physics in action. Photons generated by nuclear fusion in the core of our star take an average of 170,000 years to random walk their way to the solar surface through countless absorption and re-emission events. However, once they escape the solar photosphere, these same photons race across the 150 million kilometer distance to Earth in just 8 minutes and 20 seconds. This means the sunlight warming your face today was created in the solar core during the Pleistocene epoch, when early human ancestors were developing stone tool technologies. The speed of light fundamentally determines the scale at which physics operates across the universe. It sets the size of atoms through the fine structure constant, influences the strength of electromagnetic interactions, determines the relationship between energy and mass, governs the propagation of gravitational waves, and creates the causal structure that prevents logical paradoxes from destroying the consistency of physical law. In the realm of astronomy, the finite speed of light creates phenomena like gravitational lensing, where massive objects like galaxies or galaxy clusters bend the paths of light rays from more distant objects. This effect was first predicted by Einstein's general theory of relativity and provides one of the strongest confirmations of relativistic physics. The bending occurs because space and time are curved by mass and energy, and light follows the straightest possible paths through this curved space-time geometry. All of these effects and phenomena depend entirely on the existence of a finite, universal speed limit. This speed limit creates the rich tapestry of relativistic physics that governs everything from subatomic particles to galactic superclusters. It enables the universe to maintain causal consistency, allows for the existence of stable atoms and molecules, governs the evolution of stars and galaxies, and provides the fundamental framework within which all physical processes must operate. Remove this limit, and the entire framework of modern physics collapses, requiring completely new principles to govern how reality operates at every scale from the smallest to the largest imaginable. Imagine stepping outside on a clear night and looking up at the stars, but instead of seeing ancient light that has traveled for years or centuries or millennia to reach your eyes, you see every star, every galaxy, every cosmic event exactly as it is happening right now in this very moment. The entire observable universe would be laid bare before you in real time, creating a night sky so dynamic and chaotic that it would be almost impossible to comprehend. This is the first and most immediate consequence of infinite light speed, the complete elimination of any time delay between distant events and our observation of them. In our current universe, when we look at the North Star Polaris, we are seeing it as it appeared approximately 433 years ago. The light reaching our eyes tonight left that star during the early 1600s, when Galileo was making his first telescopic observations of the heavens. With infinite light speed, we would see Polaris exactly as it exists right now, along with any changes in its brightness, color, or position that might be occurring at this very instant. Every flicker, every stellar flare, every subtle variation would be visible immediately across the vast gulf of space. The Andromeda Galaxy, currently visible to us as it existed 2.5 million years ago, during the Pliocene epoch when our early human ancestors were developing more sophisticated stone tools, would suddenly appear in its present-day configuration. We would witness its ongoing collision and merger with our own Milky Way galaxy in real time, seeing stars being flung out of their orbits, gas clouds colliding and forming new stellar nurseries, and supermassive black holes spiraling toward each other in a cosmic dance of destruction and creation. The most distant galaxies observable by our most powerful telescopes would no longer show us the universe as it appeared when it was young and filled with the first generation of massive, short-lived stars. Instead, we would see these ancient star systems as they exist today, assuming they still exist at all. Many of the distant galaxies we currently observe may have long since been consumed by their central black holes, collided with neighboring galaxies, or simply exhausted their supplies of star-forming gas and faded into dim collections of aging red dwarf stars. Supernovae would become dramatically different spectacles to observe. Currently, when a massive star explodes in a distant galaxy, we may not detect the initial burst of light for thousands or millions of years. By the time we see the explosion, the shockwave has long since dissipated, any companion stars have already been affected, and the remnant neutron star, or black hole, has settled into its final state. With instantaneous light propagation, we would witness every supernova explosion across the entire universe at the exact moment it occurs. This would create an incredibly dynamic and violent appearing night sky. Supernovae occur in large galaxies, like our own, at a rate of roughly 1 to 3 per century, but across the entire observable universe, they explode at a rate of several per second. With infinite light speed, we would see this constant barrage of stellar explosions happening continuously, creating a sky that flickers and flares with deadly stellar violence occurring in real time across billions of light years of space. The sheer scale of this cosmic violence would be overwhelming to observe. Imagine watching dozens of stars simultaneously exploding across different galaxies, visible to the naked eye, each one briefly outshining billions of normal stars before fading over the course of weeks or months. The night sky would resemble a constant fireworks display on an unimaginable scale, with stellar deaths creating brilliant flashes of light appearing randomly across the celestial sphere at any moment. Gamma-ray bursts, the most powerful explosive events known to physics, would become immediate threats to observe and study. These catastrophic explosions, which occur when massive stars collapse into black holes, or when neutron stars collide with each other, currently appear to us as ancient events that happened billions of years ago in the distant universe. With instantaneous light propagation, we would witness these apocalyptic explosions as they happen, seeing jets of plasma accelerated to 99.99% of light speed tearing through space and obliterating anything in their paths. The intensity of gamma-ray bursts is so extreme that a single burst occurring within our own galaxy could potentially strip away Earth's ozone layer and trigger mass extinction events. Currently, we are protected by the vast distances and time delays involved, as gamma-ray bursts in distant galaxies appear to us as they occurred billions of years ago, when the universe was younger and more violent. With infinite light speed, we would see these universe-scale explosions happening in real time throughout the cosmos, creating a constant threat assessment challenge for any civilization trying to survive in such a chaotic environment. The cosmic microwave background radiation, which currently provides us with a snapshot of the universe as it appeared 380,000 years after the Big Bang, would completely disappear. This faint afterglow of creation, which permeates all of space and provides crucial evidence for the Big Bang theory, exists only because of the finite time it has taken for this ancient light to reach us. With infinite light speed, this radiation would have reached us instantaneously after the universe became transparent, leaving no trace of its existence in the present-day cosmos. Without the cosmic microwave background, our understanding of the universe's origin and early evolution would be fundamentally compromised. This radiation currently provides precise measurements of the universe's age, composition, and geometry. It reveals that ordinary matter makes up only about 5% of the universe, with dark matter comprising 27%, and dark energy accounting for the remaining 68%. The tiny temperature fluctuations in this background radiation also show us the seeds from which all large-scale cosmic structures like galaxies and galaxy clusters eventually grew. Variable stars, which change their brightness over periods of days, weeks, or months, would lose much of their scientific value for measuring cosmic distances. Currently, certain types of variable stars called Cepheids serve as standard candles for determining distances to nearby galaxies, because their brightness variations have characteristic patterns that depend on their intrinsic luminosity. With instantaneous light propagation, we would see these variations in real time, but we would lose the ability to use light travel time as a tool for measuring distances across space. Cepheid variable stars pulsate with periods ranging from a few days to several months, with longer period variables being intrinsically brighter than shorter period ones. This period luminosity relationship allows astronomers to determine the true brightness of these stars and compare it with their observed brightness to calculate their distances. Edwin Hubble used Cepheid variables to determine that the Andromeda Galaxy was far beyond our own Milky Way, revolutionizing our understanding of the universe's scale. With infinite light speed, this entire distance measurement technique would become obsolete. Binary star systems would reveal their orbital mechanics in completely different ways. Many binary systems are so distant that their orbital periods span decades or centuries from our perspective. Currently, we must observe these systems over many years to determine their orbital characteristics, stellar masses, and evolutionary states. With infinite light speed, we would see the complete orbital dance of every binary system playing out in real time, allowing us to determine stellar properties much more rapidly, but eliminating our ability to study how these systems have evolved over cosmic time. Closed binary systems, where two stars orbit each other in a matter of hours or days, would become spectacular displays of gravitational interaction. We would see material streaming from one star to its companion in real time, witness stellar flares and magnetic reconnection events as they occur, and observe the complex dynamics of accretion disks forming around white dwarf stars, neutron stars, or stellar mass black holes. The violence and beauty of these interactions would be immediately visible across the cosmos. Eclipsing binary systems would provide instantaneous measurements of stellar radii, masses, and surface temperatures. Currently, these measurements require careful timing of eclipse events over multiple orbital periods, which can take years for systems with long orbital periods. With infinite light speed, every eclipse would be observable immediately, allowing for rapid characterization of stellar properties, but eliminating the historical perspective that shows how these systems evolve over time. The death throes of massive stars would become spectacular real-time events. When stars with masses exceeding 25 times that of our own star exhaust their nuclear fuel, they undergo core collapse in a matter of seconds, followed by explosive ejection of their outer layers over periods of hours to days. Currently, we see these events only after their light has traveled for thousands or millions of years. With instantaneous propagation, we would witness the complete sequence of stellar death, from initial core collapse through the formation of supernova remnants and the birth of neutron stars or black holes. The core collapse process itself occurs incredibly rapidly, with the stellar core shrinking from the size of Earth to a diameter of about 20 kilometers in less than a second. The core temperature soars to over 100 billion degrees Celsius as protons and electrons are crushed together to form neutrons. The resulting neutron star has a density so extreme that a teaspoon of its material would weigh about 6 billion tons on Earth. With infinite light speed, we would see this entire transformation happening in real time across the universe. Following core collapse, the explosion shockwave travels outward through the star at speeds of thousands of kilometers per second, heating the stellar material to billions of degrees and creating the heavy elements that will eventually become incorporated into future generations of stars and planets. This nucleosynthesis process, which creates elements heavier than iron through rapid neutron capture, would be visible as it happens throughout the cosmos, showing us the universe's ongoing chemical evolution in real time. Active galactic nuclei, powered by supermassive black holes consuming surrounding matter, would appear as wildly fluctuating beacons of energy. These objects can vary dramatically in brightness over time, scales ranging from minutes to years, as material falls into their central black holes in an irregular and chaotic fashion. Currently, we see these variations only after significant light travel times. With infinite light speed, every flicker and flare from these cosmic monsters would be visible instantly, creating a universe filled with constantly changing sources of brilliant radiation. The accretion disks surrounding these supermassive black holes reach temperatures of millions of degrees, as gravitational energy is converted to thermal energy through friction and magnetic field interactions. Matter spiraling into the black hole experiences extreme tidal forces that stretch and compress it, heating it to the point where it emits intense X-ray and gamma-ray radiation. With instantaneous light propagation, we would see these feeding frenzies happening in real time across billions of galaxies simultaneously. Some active galactic nuclei produce relativistic jets of plasma that extend for hundreds of thousands of light years beyond their host galaxies. These jets, which travel at speeds approaching light speed, are thought to be accelerated by the rotation of the central black hole and its associated magnetic fields. With infinite light speed, we would see these jets forming, propagating, and interacting with the surrounding intergalactic medium in real time, providing unprecedented insights into black hole physics and jet formation mechanisms. Gravitational wave events would be accompanied by simultaneous electromagnetic counterparts visible across the entire cosmos. When neutron stars collide and merge, they produce both gravitational waves that ripple through space-time and intense bursts of gamma rays and other electromagnetic radiation. Currently, These electromagnetic signals may take millions of years to reach us, arriving long after we might detect the gravitational waves. With instantaneous light propagation, we would see the optical counterparts of gravitational wave events immediately, providing unprecedented insights into these catastrophic cosmic collisions. Neutron star mergers are thought to be the primary source of heavy elements like gold, platinum, and uranium in the universe. The extreme conditions during these collisions allow rapid neutron capture processes to create elements that cannot be produced in normal stellar nucleosynthesis. With infinite light speed, we would witness this cosmic alchemy happening in real time, seeing the universe's most precious metals being forged in the crucible of colliding neutron stars and immediately ejected into space to enrich future generations of stars and planets. The formation and evolution of planetary systems around distant stars would become observable in real time. Currently, we can only infer the presence of exoplanets through indirect methods like transit observations or gravitational wobbles of their host stars. The actual process of planet formation, which takes millions of years, remains largely hidden from direct observation. With infinite light speed, we could watch planets coalescing from protoplanetary disks, witness the migration of gas giant planets, and observe the bombardment phases that shape rocky worlds like Earth. Planet formation begins in the swirling disks of gas and dust that surround newly formed stars. Over millions of years, dust grains stick together to form larger and larger objects, eventually growing into asteroids, comets, and planets. With instantaneous light propagation, we would see this entire process unfolding simultaneously around thousands of young stars in our galactic neighborhood, providing direct observational evidence for theories of planet formation that are currently based largely on computer simulations and indirect evidence. The late heavy bombardment period, which occurred in our solar system approximately 4 billion years ago, when asteroids and comets rained down on the inner planets, would be visible happening around other star systems in real time. This bombardment phase is thought to have delivered much of Earth's water and organic compounds, setting the stage for the eventual emergence of life. With infinite light speed, we could observe whether this process is common around other stars and how it affects the potential habitability of rocky planets. Perhaps most remarkably, we would lose all ability to study the history and evolution of the universe itself. Cosmology as a science depends entirely on the fact that light travels at finite speed, allowing us to observe the universe at different epochs by looking at objects at different distances. With instantaneous light propagation, every part of the universe would appear as it exists right now, eliminating our window into cosmic history and making it impossible to understand how galaxies, stars, and other cosmic structures formed and evolved over billions of years of cosmic time. The concept of cosmic evolution would become meaningless without the ability to observe the universe at different stages of its development. We would lose all evidence for the Big Bang theory, the formation of the first stars and galaxies, the epoch of Ryanization when the first stars began clearing the cosmic fog of neutral hydrogen, and the gradual assembly of large-scale structure through gravitational attraction over cosmic time. The universe would appear as a static snapshot with no apparent history or evolutionary trajectory. The complete elimination of the speed of light as a finite constant would trigger the total collapse of Einstein's theory of special relativity, fundamentally rewriting the laws of physics that govern space, time, motion, and energy throughout the universe. Special relativity, formulated in 1905, is built upon two foundational principles. The laws of physics are the same in all inertial reference frames, and the speed of light in vacuum is constant for all observers, regardless of their motion. Remove the second principle by making light speed infinite, and the entire theoretical framework crumbles like a house of cards, taking with it over a century of confirmed experimental results and technological applications. Time dilation, one of the most profound and counterintuitive consequences of special relativity, would cease to exist entirely. Currently, as objects approach the speed of light, time slows down relative to stationary observers, according to the Lorentz transformation equations. A spacecraft traveling at 90% of light speed experiences time passing at roughly 45% of the normal rate compared to Earth. At 99% of light speed, time slows to about 14% of its normal flow. At 99.9% of light speed, time crawls at roughly 4.5% of its usual pace. These effects have been confirmed countless times through particle accelerator experiments, atomic clock measurements on high-speed aircraft, and observations of cosmic ray muons reaching Earth's surface despite their short lifespans. Muons created by cosmic ray impacts in the upper atmosphere normally decay in about 2 microseconds, which should prevent them from reaching ground-level detectors. However, because these muons travel at speeds approaching light speed, they experience significant time dilation that extends their lifespans enough to reach Earth's surface before decaying. With infinite light speed, the mathematical factor that creates time dilation would become meaningless. The Lorentz factor, which equals 1 divided by the square root of 1 minus velocity squared, divided by light speed squared, approaches infinity as velocity approaches light speed. But if light speed itself becomes infinite, this factor becomes simply 1 for all velocities, meaning time would pass at the same rate for all observers regardless of their motion. A spacecraft could accelerate to any velocity imaginable without experiencing any time dilation effects whatsoever. Length contraction, the complementary effect to time dilation, would also vanish completely. Objects moving at high speeds currently appear shortened in the direction of their motion, according to the same Lorentz transformation that governs time dilation. A meter stick traveling at 90% of light speed appears contracted to about 43 centimeters in length. At 99% of light speed, it shrinks to approximately 14 centimeters. At 99.9% of light speed, it contracts to just 4.5 centimeters. This effect has been observed in particle accelerators, where high-energy protons and other particles appear significantly compressed in their direction of motion. The Large Hadron Collider accelerates protons to velocities so close to light speed that they appear contracted by factors of several thousand to 1. Individual protons that normally have a diameter of about 1 femtometer appear flattened into pancake-like shapes with thicknesses measured in attometers. Without finite light speed, the mathematical relationship that creates length contraction would become trivial, with the contraction factor always equaling 1 regardless of velocity. Objects could move at arbitrarily high speeds without experiencing any change in their physical dimensions. A spacecraft accelerating to tremendous velocities would maintain its original length, width, and height as measured by any observer, eliminating one of the most fundamental consequences of relativistic motion. The relationship between mass and energy, embodied in Einstein's famous equation E equals mc squared, would require complete reformulation. In this equation, c represents the speed of light, and the factor c squared converts between mass and energy units. With infinite light speed, this conversion factor becomes infinite, creating mathematical paradoxes that would necessitate entirely new approaches to understanding the equivalence of mass and energy. Currently, this mass-energy equivalence explains how nuclear reactions release enormous amounts of energy by converting tiny amounts of matter into pure energy. In nuclear fusion reactions that power stars, 4 hydrogen nuclei combine to form 1 helium nucleus with slightly less total mass. The missing mass, equal to about 0.7% of the original hydrogen mass, converts to energy according to E equals mc squared. The enormous value of c squared, approximately 9 times 10 to the 16th power in standard units, means that even tiny mass differences release tremendous amounts of energy. Nuclear fission reactions in atomic power plants operate on the same principle, with heavy uranium or plutonium nuclei splitting into lighter fragments with slightly less total mass. The missing mass converts to kinetic energy of the fission fragments and radiation, which ultimately becomes the heat that drives electrical generators. Without a finite speed of light to provide the conversion factor between mass and energy, the fundamental physics underlying all nuclear processes would require complete reconstruction. The concept of relativistic momentum would become obsolete. Currently, momentum increases without limit as objects approach light speed, even though their velocity asymptotically approaches but never reaches the speed of light. This creates a situation where infinite energy would be required to accelerate any massive object to light speed, establishing an absolute speed limit for matter in the universe. With infinite light speed, there would be no upper bound on velocity, and momentum would return to its classical definition of simply mass times velocity. Objects could theoretically be accelerated to arbitrarily high speeds, limited only by the available energy for acceleration. Spacecraft could reach velocities that dwarf the current speed of light without requiring infinite energy or experiencing relativistic effects. The fundamental structure of spacetime itself would undergo radical transformation. Special relativity reveals that space and time are not separate entities, but form a unified four-dimensional continuum called space-time. Events that appear simultaneous to one observer may occur at different times for observers moving at different velocities, a phenomenon called the relativity of simultaneity. This effect occurs because the speed of light creates a finite rate at which information can propagate between events. When measuring the timing of distant events, observers moving at different velocities must account for the finite time it takes light signals to travel between the events and their measurement apparatus. The faster an observer moves relative to the events being measured, the more the apparent timing of those events shifts. With infinite light speed, information could propagate instantaneously between any 2 points in the universe, eliminating the relativity of simultaneity entirely. All observers, regardless of their motion, would agree on the timing of distant events. The concept of now would become absolute and universal, applying simultaneously across all of space rather than being relative to each observer's reference frame. This would restore the Newtonian concept of absolute time, where a universal clock ticks at the same rate throughout the universe, and all observers can agree on whether two distant events occurred simultaneously. Space and time would once again become separate entities, rather than the unified spacetime of relativity. The elegant four-dimensional geometry of spacetime, described by Minkowski diagrams and Lorentz transformations, would collapse back into the simpler three-dimensional space plus one-dimensional time of classical physics. The principle of causality, which requires that cause must precede effect, would face serious challenges in a universe with infinite signal propagation speed. Currently, the finite speed of light creates light cones that define which events can influence each other. Events outside each other's light cones cannot have causal relationships, because no signal can travel between them faster than light. With infinite light speed, every event in the universe could potentially influence every other event instantaneously, regardless of their spatial separation. This could create situations where effects appear to precede their causes, leading to logical paradoxes that would threaten the consistency of physical law. The universe would require new mechanisms to preserve causal ordering and prevent paradoxical situations from arising. Particle physics would undergo revolutionary changes, as the standard model of particle physics depends heavily on relativistic principles. The relationship between energy and momentum for massless particles like photons is currently given by E equals pc, where p is momentum and c is the speed of light. With infinite light speed, this relationship would become undefined, requiring new approaches to understanding electromagnetic radiation and other massless phenomena. The concept of rest mass versus relativistic mass would lose all meaning. Currently, objects have an invariant rest mass that remains constant regardless of their motion. while their relativistic mass increases with velocity according to the Lorentz factor. At high speeds, the relativistic mass can become arbitrarily large, even though the rest mass remains unchanged. With infinite light speed, relativistic mass would always equal rest mass, regardless of velocity. High-energy particle physics experiments would produce dramatically different results. Currently, when particles are accelerated to near light speed in colliders like the Large Hadron Collider, their increased relativistic mass allows them to create new particles through Einstein's mass-energy equivalence. Collisions between protons with relativistic energies of several tera-electron volts can create particles with masses hundreds of times greater than the original protons. Without relativistic mass increase, particle collisions would be limited to creating particles with masses no greater than the rest masses of the colliding particles. The rich zoo of exotic particles discovered through high-energy physics, including the Higgs boson, W and Z bosons, and various quarks and leptons, might never have been observed because the energy densities required for their creation would be impossible to achieve without relativistic effects. Electromagnetic radiation itself would behave in fundamentally different ways. Currently, the energy of electromagnetic radiation is related to its frequency through Planck's constant, while its momentum is related to its energy through the speed of light. Photons carry both energy and momentum despite having zero rest mass. With infinite light speed, the relationship between electromagnetic energy and momentum would require complete reformulation. The Doppler effect, which causes electromagnetic radiation to shift in frequency when sources and observers move relative to each other, depends on relativistic principles for accurate description at high velocities. Currently, light from objects moving away from us appears redshifted to lower frequencies, while light from approaching objects appears blue-shifted to higher frequencies. These effects become extreme for objects moving at significant fractions of light speed. With infinite light speed, the relativistic Doppler effect would disappear entirely, though a classical Doppler effect might still exist. The cosmic redshift that provides evidence for the expansion of the universe and allows measurement of galactic recession velocities would require reinterpretation through entirely different physical mechanisms. The theoretical foundations of quantum field theory, which successfully describes the electromagnetic, weak, and strong nuclear forces, incorporate special relativity as a fundamental requirement. Quantum field theories must be Lorentz invariant, meaning they produce the same physical predictions regardless of the observer's velocity. This requirement severely constrains the possible forms that physical theories can take and has guided the development of the standard model of particle physics. Without special relativity, quantum field theory would require complete reconstruction from first principles. The elegant mathematical framework that unifies quantum mechanics with special relativity, including concepts like antiparticles, spin, and gauge symmetries, might not emerge naturally in a universe without relativistic constraints. The fundamental forces of nature could operate according to entirely different principles that we can barely imagine. The concept of space-time curvature, which forms the foundation of general relativity and our understanding of gravity, emerges naturally from special relativity through the equivalence principle. Without special relativity as a prerequisite, the geometric interpretation of gravity as curved space-time would lose its theoretical motivation. Gravity might operate through entirely different mechanisms, possibly resembling Newton's instantaneous action at a distance rather than Einstein's geometric curvature of spacetime. Perhaps most fundamentally, the entire philosophical framework for understanding the relationship between space, time, matter, and energy would require reconstruction. Special relativity revealed that these apparently separate concepts are actually different aspects of a unified reality. Without this unification, physics would fragment back into separate theories for mechanics, electromagnetism, thermodynamics, and other phenomena, losing the elegant simplicity and predictive power that comes from understanding the deep connections between seemingly disparate physical processes. The transformation of light speed from finite to infinite would fundamentally alter the nature of gravity itself, revolutionizing how this most familiar yet mysterious force operates throughout the universe. In Einstein's general theory of relativity, gravity is not a force in the traditional sense, but rather the curvature of space-time, caused by the presence of mass and energy. This curvature propagates through space at exactly the speed of light, creating gravitational waves that carry information about changes in massive objects across the cosmos. Remove the finite speed limit, and gravity would transform from a geometric property of curved space-time into something entirely different, possibly resembling Newton's original conception of instantaneous action at a distance, but with consequences that would reshape the entire cosmic landscape. Currently, when massive objects accelerate or undergo sudden changes in their mass distribution, they create ripples in the fabric of space-time that propagate outward at light speed. These gravitational waves were predicted by Einstein in 1916 and finally detected directly by the Laser Interferometer Gravitational Wave Observatory in 2015, confirming one of the last major predictions of general relativity. The detection of gravitational waves from colliding black holes and neutron stars has opened an entirely new window for observing the universe, allowing astronomers to study cosmic events that produce little or no electromagnetic radiation. With infinite light speed, gravitational waves would propagate instantaneously throughout the universe, fundamentally changing how gravitational information travels between objects. Any change in the mass or motion of an object would immediately influence the gravitational field at all points in space, no matter how distant. This would restore Newton's concept of gravity as an instantaneous force acting directly between masses, but within the context of a universe that has already been transformed by the elimination of relativistic effects. The implications for orbital mechanics would be profound and far-reaching. Currently, planetary orbits are stable, partly because gravitational changes propagate at finite speed, creating a form of cosmic friction that gradually removes energy from orbital systems through gravitational wave emission. When two massive objects orbit each other, they continuously emit gravitational waves that carry away orbital energy, causing the orbits to slowly decay over enormous timescales. This effect is most pronounced for extremely compact objects like neutron stars or black holes orbiting close to each other. The famous Hulse-Taylor binary pulsar, discovered in 1974, consists of two neutron stars orbiting each other with a period of about 7¾ hours. Careful timing measurements over decades have shown that this orbital period is decreasing by exactly the amount predicted by general relativity due to energy loss through gravitational wave emission. With instantaneous gravity, this orbital decay mechanism would disappear entirely. Binary systems would no longer lose energy through gravitational wave emission, potentially making them stable over much longer timescales. However, the instantaneous response of gravity to changes in mass distribution could create entirely new forms of orbital instability that do not exist in our current universe. Consider what would happen when a massive star explodes as a supernova. Currently, the explosion ejects most of the star's mass into space over a period of hours to days, while the gravitational effects of this mass loss propagate outward at light speed. Planets orbiting the star experience the reduced gravitational pull only after the gravitational waves from the explosion reach their orbital locations. This delay can help stabilize planetary orbits during the chaotic explosion process. With infinite gravity propagation speed, planets would feel the effects of the stellar mass loss instantaneously as the explosion occurs. The sudden reduction in gravitational attraction could cause planets to immediately fly out of their orbits, transforming supernova explosions into cosmic billiard ball events that scatter planetary systems across interstellar space in real time. The behavior of binary star systems would become dramatically different. Currently, when one star in a binary system explodes as a supernova, the sudden mass loss can unbind the binary, sending the surviving star flying through space as a runaway star. The neutron star or black hole left behind by the explosion may also receive a kick from asymmetric neutrino emission during the explosion, further complicating the dynamics. With instantaneous gravity, these disruption events would happen immediately rather than being mediated by finite-speed gravitational wave propagation. The surviving components of disrupted binary systems would instantly feel the gravitational effects of mass loss and explosion asymmetries, potentially creating more violent and unpredictable outcomes than occur in our current universe. Black hole mergers would become instantaneous gravitational catastrophes rather than the gradual spiral in spirals we observe today. Currently, when two black holes orbit each other, they gradually lose energy through gravitational wave emission, causing their orbits to shrink over millions or billions of years. As they get closer together, the orbital decay accelerates, and the final plunge occurs over a timescale of milliseconds, producing intense gravitational waves that can be detected by interferometers on Earth. With infinite gravity propagation speed, black hole mergers might occur through entirely different mechanisms. The instantaneous gravitational response could prevent the gradual spiral-in-spiral phase entirely, possibly causing binary black holes to merge suddenly when they approach within a certain critical distance. The dynamics of these mergers would be governed by entirely new physics that we can barely imagine. The formation and evolution of galaxies would be fundamentally altered by instantaneous gravity. Currently, galaxy formation occurs through the gradual gravitational collapse of dark matter halos over hundreds of millions of years. Dark matter particles interact primarily through gravity, slowly clumping together under their mutual gravitational attraction to form the scaffolding upon which galaxies eventually form. With instantaneous gravitational interactions, this process could occur much more rapidly and violently. Dark matter clumps could collapse catastrophically rather than gradually, potentially creating galaxy formation events that happen over much shorter timescales. The complex dance of gravitational interactions that shapes galactic structure, including the formation of spiral arms and central bars, would be governed by entirely different dynamics. Galactic collisions would become even more spectacular and chaotic events. When galaxies like our Milky Way and the Andromeda Galaxy collide, the gravitational interactions between their billions of stars create complex tidal forces that reshape both galaxies over hundreds of millions of years. Currently, these interactions are mediated by gravitational signals that propagate at light speed, creating a form of cosmic choreography where different parts of each galaxy respond to gravitational changes at different times. With instantaneous gravity, galactic collisions would become synchronous throughout both galaxies simultaneously. Every star in both galaxies would instantly feel the gravitational effects of every other star, creating chaotic, gravitational environments that could scatter stars in completely unpredictable directions. The beautiful spiral structure and organized rotation of galaxies might not be able to form or persist in such an environment. The stability of galaxy clusters, the largest gravitationally bound structures in the universe, would also be affected by instantaneous gravity. These massive collections of hundreds or thousands of galaxies are held together by their mutual gravitational attraction, modified by the mysterious effects of dark matter and dark energy. Currently, the finite speed of gravitational interactions helps stabilize these structures by preventing rapid gravitational fluctuations from propagating instantly throughout the cluster. With infinite gravity propagation speed, galaxy clusters might become more susceptible to gravitational instabilities that could cause them to fly apart or collapse into supermassive central objects. The delicate balance between gravitational attraction and cosmic expansion that maintains galaxy cluster structure might not be achievable with instantaneous gravitational interactions. The behavior of tidal forces would change dramatically throughout the universe. Currently, tidal effects result from the difference in gravitational acceleration between different parts of an extended object. The side of Earth facing the Moon experiences slightly stronger lunar gravity than Earth's center, while the side facing away from the Moon experiences slightly weaker gravity. These differences create the ocean tides that rise and fall twice each day. With instantaneous gravity, tidal effects would respond immediately to any changes in the positions or masses of gravitating objects. The complex tidal interactions between Earth, Moon, and various other solar system bodies would become perfectly synchronized, potentially creating more extreme tidal phenomena or entirely different tidal patterns than we observe today. Planetary ring systems like those around Saturn would be subject to instantaneous gravitational perturbations from their parent planets and various moons. Currently, the intricate structure of Saturn's rings, with their thousands of individual ringlets separated by gaps, results from complex gravitational resonances with Saturn's moons that develop over long time scales. With instantaneous gravity, these ring systems might not be able to maintain their delicate structure, possibly collapsing into more chaotic configurations or being ejected from the planetary system entirely. The phenomenon of gravitational lensing, where massive objects bend the paths of light rays from more distant sources, would require complete reinterpretation in a universe with infinite light speed. Currently, gravitational lensing occurs because massive objects curve space-time, and light follows the straightest possible paths through this curved geometry. The bending of light by gravity has been confirmed through countless observations and provides one of the strongest confirmations of general relativity. With infinite light speed, light would travel instantaneously from source to observer along perfectly straight lines through flat space-time. The gravitational lensing effects that currently allow astronomers to study dark matter distribution, discover distant galaxies, and measure cosmic distances would disappear entirely. Alternative methods for detecting dark matter and studying large-scale cosmic structure would be necessary. The concept of event horizons around black holes would become meaningless in a universe with instantaneous information propagation. Currently, event horizons represent the boundary beyond which no information can escape a black hole because even light traveling at maximum speed cannot overcome the intense gravitational field. Information about events occurring inside the event horizon can never reach outside observers, creating fundamental limits on what can be known about black hole interiors. With infinite light speed, information could theoretically escape from any location, no matter how deep within a gravitational field. The concept of black holes as regions of space-time from which nothing can escape would require complete reformulation. These objects might become visible throughout their entire volume, revealing the internal structure and dynamics that are currently hidden behind event horizons. Hawking radiation, the theoretical process by which black holes slowly evaporate by emitting particles due to quantum effects near the event horizon, would also require reinterpretation. This radiation depends on the existence of event horizons and the finite speed of light to create the conditions necessary for virtual particle pairs to be separated and converted into real particles. Without event horizons or finite light speed, the mechanism producing Hawking radiation might not exist at all. The GPS satellite navigation system, which currently requires corrections for both special and general relativistic effects, would face entirely different challenges in a universe with instantaneous gravity and infinite light speed. Currently, GPS satellites experience time dilation due to their orbital velocity and gravitational time dilation due to their position in Earth's gravitational field. These effects cause satellite clocks to run at different rates than ground-based clocks, requiring constant correction to maintain positioning accuracy. With infinite light speed and no relativistic effects, GPS satellites would not experience time dilation, but they would face new challenges from instantaneous gravitational interactions. Any changes in Earth's mass distribution, such as seasonal ice melting or large earthquakes, would instantly affect satellite orbits rather than taking time to propagate as gravitational waves. This could create new sources of orbital perturbation that would need to be accounted for in navigation calculations. The entire field of gravitational physics would require reconstruction from first principles. The elegant geometric interpretation of gravity as space-time curvature, which has guided theoretical physics for over a century, would lose its foundation without finite light speed to create the relativistic effects that motivate curved space-time geometry. Gravity might operate through entirely different mechanisms that bear little resemblance to either Newtonian instantaneous action at a distance or Einsteinian space-time curvature. Perhaps most profoundly, the universe might not be able to support the complex hierarchical structure of cosmic organization that we observe today. The delicate balance between gravitational attraction, cosmic expansion, and finite signal propagation speeds that allows the formation of planets, stars, galaxies, and galaxy clusters might not be achievable with instantaneous gravitational interactions. The cosmos might collapse into a much simpler and more chaotic state where complex structures cannot form or persist over cosmological timescales. The transformation of light speed from a finite constant to an infinite value would revolutionize communication and technology in ways that would fundamentally reshape human civilization and our relationship with the cosmos. Every form of information transmission, from simple radio signals to complex quantum communication protocols, depends on the finite speed of electromagnetic radiation to function properly. Remove this fundamental limit, and the entire technological infrastructure that supports modern society would require complete reconstruction, while simultaneously opening possibilities for communication and exploration that seem like pure science fiction from our current perspective. Interplanetary communication would be transformed from a patient exercise in astronomical timing into an instantaneous conversation across the solar system. Currently, when NASA mission controllers send commands to the Perseverance rover on Mars, they must wait anywhere from 4 minutes to 24 minutes for their signals to travel the distance between Earth and Mars, depending on the relative positions of the two planets in their orbits. This communication delay makes real-time control of Mars missions impossible, forcing engineers to design autonomous systems that can operate independently for extended periods. The Mars helicopter Ingenuity, for example, must execute its entire flight plan autonomously because radio signals from Earth cannot provide real-time control input. Mission planners upload flight instructions hours or days in advance, then wait for confirmation data to return from the helicopter's sensors and cameras. Each flight becomes a carefully choreographed sequence that must account for every possible contingency, since human operators cannot intervene if something goes wrong. With infinite light speed, controlling Mars rovers and helicopters would become as simple as operating remote-controlled vehicles in your backyard. Engineers could pilot rovers across the Martian landscape in real time, responding immediately to obstacles, interesting geological features, or equipment malfunctions. The autonomous artificial intelligence systems currently required for Mars exploration could be replaced by direct human control, allowing for much more flexible and responsive mission operations. Communication with outer solar system missions would be even more dramatically transformed. The Voyager 1 spacecraft, currently the most distant human-made object at over 24 billion kilometers from Earth, experiences a communication round-trip time of more than 45 hours. Commands sent to Voyager today will not be acknowledged until nearly 2 days later. The New Horizons mission, which flew by Pluto in 2015, required over 9 hours for signals to travel between Earth and the spacecraft during the encounter. With instantaneous communication, these distant missions could be controlled as easily as satellites in Earth orbit. Scientists could redirect spacecraft trajectories, modify instrument settings, and respond to unexpected discoveries in real time, regardless of distance. The Grand Tour missions like Voyager, which were carefully planned decades in advance to take advantage of rare planetary alignments, could be replaced by more flexible exploration strategies that adapt to discoveries as they happen. Interstellar communication would leap from the realm of theoretical possibility into practical reality. The Breakthrough Listen project currently searches for radio signals from extraterrestrial civilizations, but any detected signals would represent communications from years, decades, or centuries in the past, depending on their distance. A radio signal from Proxima Centauri, our nearest stellar neighbor at 4.24 light-years away, would take over 4 years to reach Earth, making any form of conversation impossible within human lifetimes. With infinite light speed, interstellar conversation becomes theoretically possible. A message sent to Proxima Centauri could receive an immediate response, allowing real-time communication with any civilizations that might exist around nearby stars. The search for extraterrestrial intelligence would be transformed from passive listening for ancient signals into active, real-time communication protocols that could establish immediate contact with alien civilizations anywhere in the galaxy. The implications for interstellar exploration would be equally profound. Current plans for interstellar missions envision spacecraft that travel for decades or centuries to reach nearby star systems, with no possibility of real-time communication or control once they leave the solar system. The proposed Breakthrough Starshot project aims to send tiny spacecraft to Proxima Centauri, using light sails accelerated by powerful laser arrays. But these spacecraft would take 20 years to reach their destination and another 4 years to send data back to Earth. With instantaneous communication, interstellar missions could maintain constant contact with Earth regardless of their distance. Spacecraft exploring other star systems could transmit scientific data, high-resolution images, and telemetry information in real time, allowing Earth-based scientists to participate directly in exploration of exoplanets and alien environments. Mission control could adjust spacecraft trajectories, modify scientific objectives, and respond to unexpected discoveries as if the spacecraft were orbiting Mars rather than traveling to distant stars. The internet and global communications infrastructure would undergo fundamental changes with infinite information propagation speed. Currently, internet traffic traveling around the world through undersea fiber optic cables experiences latency of roughly 67 milliseconds for signals traveling halfway around Earth. This delay results from light traveling through optical fiber at approximately 2/3 of vacuum light speed due to the refractive index of glass. High-frequency financial trading operations spend billions of dollars to reduce these communication delays by even small fractions of a millisecond. Trading firms install microwave relay towers and lay dedicated fiber optic cables along the shortest possible paths between major financial centers, seeking any advantage that faster information transmission can provide. Some firms have even investigated using neutrino beams to transmit trading data through the Earth's core to avoid the longer path around the planet's surface. With infinite light speed, global internet latency would become essentially zero regardless of distance. A video call between New York and Sydney would have no more delay than a conversation between people in the same room. Online gaming could support perfect real-time interaction between players anywhere on Earth. High-frequency trading would lose its technological arms race for faster communication, since all traders would have access to the same instantaneous information regardless of their geographic location. Satellite communication systems would be revolutionized by the elimination of signal propagation delays. Current geostationary communication satellites orbit at an altitude of approximately 35,786 kilometers above Earth's equator, creating a round-trip signal delay of about half a second between ground stations and satellites. This delay is noticeable in satellite phone conversations and creates challenges for certain types of real-time communication applications. With infinite light speed, satellite communication would become as responsive as terrestrial fiber optic networks. Satellite internet services like Starlink could provide latency identical to ground-based broadband, regardless of satellite altitude or orbital position. Remote areas of Earth that currently rely on geostationary satellite communication would gain access to the same real-time communication capabilities as major metropolitan areas with extensive fiber optic infrastructure. The design of computer processors and electronic circuits would require fundamental reconceptualization in a world with infinite signal propagation speed. Modern microprocessors operate at clock frequencies measured in gigahertz, where each clock cycle lasts only a few nanoseconds. During a single clock cycle of a 3 GHz processor, electromagnetic signals can travel only about 10 centimeters through copper conductors or vacuum. This speed of light limitation creates significant challenges for processor designers, who must carefully lay out circuits to ensure that signals can propagate between different parts of the chip within a single clock cycle. As processors become faster and more complex, these timing constraints become increasingly difficult to satisfy. Advanced processors use techniques like pipeline parallelism and predictive execution to work around the fundamental speed limitations imposed by finite signal propagation. With infinite signal propagation speed, these design constraints would disappear entirely. Processors could operate at arbitrarily high clock frequencies without concern for signal propagation delays between different circuit components. Computer architectures could become much more distributed and parallel, since communication between processing elements would not be limited by physical distance or signal travel time. Quantum communication systems, which currently rely on the finite speed of light to ensure security, would require complete redesign. Quantum key distribution protocols like BB84 use the finite propagation time of photons to detect eavesdropping attempts. Any interception of quantum-encoded photons necessarily disturbs their quantum states, allowing the communicating parties to detect the presence of an eavesdropper by measuring the error rate in received quantum information. With infinite light speed, the timing-based security mechanisms that protect quantum communication would become meaningless. New quantum cryptography protocols would need to be developed that do not rely on finite signal propagation speeds to ensure security. The entire field of quantum information theory might need to be reconstructed from first principles to account for instantaneous information transmission. Radio astronomy would face both opportunities and challenges in a universe with infinite electromagnetic propagation speed. Currently, radio telescopes detect signals from distant cosmic sources that have traveled for millions or billions of years to reach Earth. These observations provide crucial information about the history and evolution of the universe, allowing astronomers to study cosmic conditions at different epochs. With instantaneous radio wave propagation, radio telescopes would observe the universe in real time rather than looking back through cosmic history. This would eliminate the ability to study cosmic evolution through radio observations, but it would also provide unprecedented access to dynamic astronomical phenomena as they occur. Radio astronomers could observe stellar explosions, black hole feeding events, and other cosmic catastrophes in real time throughout the observable universe. The Very Long Baseline Interferometry technique, which combines signals from radio telescopes separated by thousands of kilometers to achieve extremely high angular resolution, relies on precise timing of radio wave arrivals at different telescopes. With infinite signal propagation speed, this technique would require fundamental modification, as all radio signals would arrive simultaneously at every telescope regardless of their geometric arrangement. Navigation systems like GPS would need complete redesign to function with instantaneous signal propagation. The current GPS system works by measuring the time it takes radio signals to travel from multiple satellites to a receiver on Earth's surface. By comparing the arrival times of signals from at least 4 satellites with known positions and synchronized clocks, GPS receivers can calculate their precise location through trilateration. With infinite signal propagation speed, all GPS signals would arrive at receivers instantaneously, eliminating the time-based measurements that enable position calculation. New navigation principles would need to be developed, possibly based on signal phase relationships, frequency differences, or entirely different physical phenomena. The incredible precision of modern GPS systems, which can determine positions to within a few centimeters, might not be achievable using alternative navigation methods. Deep space navigation for interplanetary missions currently relies on precise measurements of radio signal travel times between Earth and spacecraft to determine spacecraft positions and velocities. The Deep Space Network uses enormous radio antennas to track spacecraft throughout the solar system, measuring tiny Doppler shifts in radio frequencies to monitor spacecraft motion and plan trajectory corrections. With instantaneous communication, these navigation techniques would become obsolete. New methods for determining spacecraft positions and velocities would be necessary, possibly based on gravitational field measurements, stellar parallax observations, or other physical phenomena that do not depend on finite signal propagation speeds. The precision navigation required for complex missions like planetary flybys and orbital insertions might become much more challenging without the ability to use signal timing for position determination. Scientific research collaboration would be transformed by instantaneous global communication. Currently, international research projects face coordination challenges due to communication delays and time zone differences. Large-scale experiments like those conducted at CERN require careful synchronization between research teams located around the world, with data sharing and analysis often delayed by the finite speed of internet communication. With infinite communication speed, scientific collaboration could become truly instantaneous regardless of geographic distance. Research teams in different countries could work together as if they were in the same laboratory, sharing data, coordinating experiments, and analyzing results in real time. The pace of scientific discovery might accelerate dramatically as communication barriers between researchers are eliminated. Perhaps most remarkably, the elimination of communication delays would fundamentally change humanity's relationship with space exploration and the search for life beyond Earth. The lonely isolation of deep space missions, where spacecraft travel for years or decades with minimal contact from Earth, would be replaced by constant connectivity and real-time collaboration between Earth-based scientists and robotic explorers throughout the solar system and beyond. The dream of interstellar communication would become an immediate reality, potentially opening conversations with alien civilizations that have remained silent only because of the impossibly long communication delays imposed by finite light speed. The infinite speed of light would completely obliterate our current methods for understanding the universe's structure, age, and evolution, fundamentally destroying the entire foundation of modern cosmology and forcing humanity to reconstruct our picture of cosmic reality from scratch. Every measurement technique that astronomers use to probe the large-scale properties of the universe depends critically on the finite speed of light to provide distance information, temporal sequencing, and evolutionary context. Remove this cosmic speed limit, and the elegant framework of Big Bang cosmology, cosmic expansion, dark matter, and dark energy would collapse into an incomprehensible puzzle, with missing pieces scattered across an instantaneous and ahistorical cosmos. Currently, astronomers measure cosmic distances using a carefully calibrated sequence of overlapping techniques known as the cosmic distance ladder. This intricate measurement system begins with direct geometric methods like stellar parallax for nearby stars, then progresses through standard candles like Cepheid variable stars and Type Ia supernovae to reach the most distant galaxies observable in the universe. Each rung of this distance ladder depends on light travel time to provide the fundamental relationship between distance and observable brightness. Stellar parallax, the foundational technique for measuring distances to nearby stars, works by observing the apparent shift in a star's position as Earth orbits around our central star over the course of a year. This tiny angular shift, typically measured in thousandths of an arcsecond, occurs because light from the star takes a finite time to reach Earth, and our changing orbital position means we observe the star from slightly different angles at different times of the year. With infinite light speed, stellar parallax would become meaningless as a distance measurement technique. Light from distant stars would reach Earth instantaneously, regardless of our orbital position, eliminating the time delay that creates the observable parallax shift. Astronomers would lose their most direct and reliable method for measuring stellar distances, undermining the entire foundation of the cosmic distance ladder. Cepheid variable stars, which serve as standard candles for measuring distances to nearby galaxies, rely on the period luminosity relationship discovered by Henrietta Swan Leavitt in 1912. These pulsating stars have intrinsic brightnesses that correlate with their pulsation periods, allowing astronomers to determine their true luminosity and compare it with their observed brightness to calculate distance. This technique enabled Edwin Hubble to discover that the Andromeda Galaxy lies far beyond our own Milky Way, revolutionizing our understanding of the universe's scale. With infinite light speed, Cepheid variables would still pulsate with their characteristic periods, but the light travel time component that enables distance measurement would disappear. Astronomers could observe the pulsations in real time, but they would lose the ability to use the relationship between intrinsic and observed brightness to determine distance. The technique that revealed the true scale of the universe and established the existence of other galaxies would become obsolete. Type Ia supernovae, the thermonuclear explosions of white dwarf stars that serve as the most powerful standard candles for measuring cosmic distances, would lose their utility for cosmological measurements. These stellar explosions have remarkably consistent peak brightnesses because they occur when white dwarf stars reach a critical mass limit known as the Chandrasekhar limit. The uniformity of these explosions allows astronomers to use them as cosmic lighthouses for measuring distances to galaxies billions of light years away. The 1998 discovery that distant Type Ia supernovae appear dimmer than expected led to the shocking realization that the universe's expansion is accelerating, driven by the mysterious dark energy that comprises roughly 68% of the universe's total energy density. This Nobel Prize-winning discovery fundamentally changed our understanding of cosmic evolution and the ultimate fate of the universe. With infinite light speed, Type Ia supernovae would still explode with their characteristic brightness, but astronomers would observe all of these explosions in real time, rather than seeing them as they occurred millions or billions of years ago. The dimming effect that revealed cosmic acceleration results from observing supernova at different cosmic epochs when the universe had different expansion rates. Without the ability to look back in time through finite light travel, this crucial evidence for dark energy would vanish entirely. The cosmic microwave background radiation, the afterglow of the Big Bang that provides our most direct observational window into the early universe, would disappear completely in a universe with infinite light speed. This faint radiation, discovered accidentally by Arno Penzias and Robert Wilson in 1964, represents photons that have been traveling through space for approximately 13.8 billion years, since the universe first became transparent to electromagnetic radiation. The cosmic microwave background provides exquisitely precise measurements of fundamental cosmological parameters, including the universe's age, geometry, and composition. Tiny temperature fluctuations in this radiation, measured to precisions of millionths of a degree, reveal the seeds from which all large-scale cosmic structure eventually grew through gravitational amplification over billions of years. With infinite light speed, these ancient photons would have reached us instantaneously after the universe became transparent, leaving no trace of their existence in the present-day cosmos. The cosmic microwave background, which has been called the most perfect blackbody spectrum ever observed and provides the strongest evidence for the Big Bang theory, would simply not exist. Cosmologists would lose their primary tool for understanding the universe's origin and early evolution. The concept of the observable universe would become meaningless in a cosmos with instantaneous light propagation. Currently, the observable universe has a radius of approximately 46.5 billion light-years, representing the maximum distance from which light has had time to reach us since the Big Bang occurred roughly 13.8 billion years ago. This creates a cosmic horizon beyond which we cannot observe any objects or events, regardless of how powerful our telescopes become. With infinite light speed, there would be no cosmic horizon limiting our observations. We could potentially see every object in the entire universe simultaneously, regardless of distance. However, this apparent advantage would come at the cost of losing all temporal information about cosmic evolution. Instead of observing a rich tapestry of cosmic history by looking at objects at different distances, we would see only a single instantaneous snapshot of the universe as it exists right now. The Hubble constant, which measures the current rate of cosmic expansion, would become impossible to determine using current methods. Edwin Hubble's original discovery of cosmic expansion relied on measuring both the distances and recession velocities of galaxies, revealing the linear relationship between distance and velocity that bears his name. This relationship provides direct evidence that space itself is expanding, carrying galaxies away from each other like raisins in rising bread dough. Distance measurements depend on light travel time to establish the cosmic distance ladder, while velocity measurements rely on the Doppler shift of spectral lines in galactic light. With infinite light speed, both of these measurement techniques would require fundamental modification. The redshift of distant galaxies might still be observable, but interpreting this redshift as evidence for cosmic expansion would require entirely new theoretical frameworks. The age of the universe, currently determined to be 13.77 billion years, based on observations of the cosmic microwave background and type Ia supernovae, would become impossible to measure using electromagnetic observations. This age determination relies on extrapolating the current expansion rate backward in time to determine when the universe had zero size, marking the moment of the Big Bang. Without the ability to observe cosmic expansion through distance and velocity measurements, determining the universe's age would require entirely different approaches. Perhaps gravitational wave observations or other non-electromagnetic phenomena could provide alternative methods for cosmic age determination. But the elegant consistency between multiple independent measurement techniques that currently supports our understanding of cosmic chronology would be lost. The discovery and characterization of dark matter would face enormous challenges without the ability to observe gravitational lensing effects. Currently, astronomers detect dark matter primarily through its gravitational influence on visible matter and light. Gravitational lensing, where massive concentrations of dark matter bend the paths of light rays from more distant galaxies, provides some of the strongest evidence for dark matter's existence and allows detailed mapping of dark matter distribution throughout the universe. With infinite light speed traveling along perfectly straight paths through flat space-time, gravitational lensing effects would disappear entirely. The spectacular images of multiply-lensed quasars and gravitationally distorted background galaxies that provide crucial insights into dark matter structure would not exist. Alternative methods for detecting and studying dark matter would be necessary, possibly based on its gravitational effects on the motions of stars and gas within galaxies. The cosmic web, the largest scale structure in the universe consisting of vast filaments of dark matter and galaxies separated by enormous voids, might not be observable using current techniques. The three-dimensional mapping of this structure relies on measuring both the positions and distances of millions of galaxies using redshift surveys and other distance determination methods that depend on finite light speed. Without reliable distance measurements, constructing three-dimensional maps of cosmic structure would become extremely challenging. The beautiful visualization of the cosmic web, revealed by surveys like the Sloan Digital Sky Survey, showing how galaxies are arranged in vast interconnected filaments surrounding enormous empty voids, might not be achievable without alternative distance measurement techniques. Galaxy formation and evolution studies would lose their most powerful observational tool, the ability to observe galaxies at different cosmic epochs by looking at objects at different distances. Currently, astronomers can study how galaxies have changed over cosmic time by observing nearby galaxies as they appear today and comparing them with distant galaxies as they appeared billions of years ago when the universe was much younger. This technique has revealed that early galaxies were typically smaller, more irregular, and contained higher rates of star formation than modern galaxies. The gradual assembly of large galaxies through mergers with smaller companions has been directly observed by comparing galaxy populations at different redshifts. The evolution of galaxy morphology, stellar populations, and chemical composition over cosmic time provides crucial insights into how cosmic structure has grown and matured. With infinite light speed, all galaxies would be observed in their present-day configurations, eliminating the ability to study galactic evolution through look-back time observations. Understanding how galaxies form and evolve would require entirely different observational approaches, possibly based on detailed studies of stellar populations and chemical abundances within individual galaxies. The measurement of cosmic curvature, which determines whether the universe is geometrically flat, closed, or open, relies on precise observations of the cosmic microwave background and distant supernova. These measurements indicate that the universe is remarkably close to perfect geometric flatness, with any curvature constrained to be less than 1% of the critical value that separates closed and open geometries. Without the cosmic microwave background and reliable distance measurements to distant supernovae, determining cosmic curvature would require alternative approaches. The geometric tests that currently support our understanding of cosmic flatness would be impossible to perform, leaving fundamental questions about the universe's global geometry unanswered. Perhaps most profoundly, the entire concept of cosmic evolution would become observationally inaccessible. The remarkable story of how the universe has changed from a hot, dense, nearly uniform state shortly after the Big Bang to the complex, structured cosmos we observe today depends entirely on our ability to observe different cosmic epochs through finite light travel times. The progression from the cosmic dark ages through the formation of the first stars, the epoch of reionization, the assembly of the first galaxies, and the gradual construction of large-scale structure over billions of years represents one of the greatest intellectual achievements in human history. This epic narrative of cosmic evolution, supported by multiple independent lines of observational evidence, would become invisible in a universe with infinite light speed. Cosmology would be forced to develop entirely new theoretical frameworks and observational techniques to understand the universe's nature and history. The elegant mathematical models of Big Bang cosmology, cosmic inflation, and structure formation that currently provide coherent explanations for a vast range of cosmic phenomena would lose their observational foundation. Humanity would face the enormous challenge of reconstructing our understanding of cosmic reality using fundamentally different tools and conceptual approaches that we can barely imagine from our current perspective. The elimination of the speed of light as a finite constant would create catastrophic challenges for the fundamental logical consistency of the universe itself, potentially allowing violations of causality that could tear apart the rational fabric of reality and create paradoxes that threaten the very possibility of coherent physical law. In our current universe, the finite speed of light serves as a cosmic referee that enforces the rule that cause must always precede effect, preventing logical contradictions from destroying the consistency of physical processes. Remove this universal speed limit, and we enter a realm where effects could potentially precede their causes, where information could travel backward in time, and where the logical foundation that makes scientific understanding possible could collapse into an incomprehensible maze of temporal paradoxes and causal loops. Currently, the finite speed of light creates what physicists call light cones, which are geometric structures in spacetime that define the causal relationships between events. Any event in spacetime sits at the vertex of two cone-shaped regions. The past light cone contains all events that could have influenced the given event, while the future light cone contains all events that the given event could potentially influence. Events outside these light cones are causally disconnected, meaning they cannot influence each other because no signal traveling at or below light speed can connect them. This causal structure ensures that the universe maintains logical consistency by preventing faster than light communication or travel from creating paradoxical situations. If information could travel faster than light, it would be possible under certain circumstances to send messages into the past, creating the potential for logical contradictions known as grandfather paradoxes. The classic formulation involves traveling back in time and preventing your own birth, creating the logical impossibility that you both exist and do not exist simultaneously. With infinite light speed, information could propagate instantaneously between any 2 points in the universe, regardless of their spatial separation. This would effectively eliminate the light cone structure that maintains causal ordering, potentially allowing information to flow in ways that violate the fundamental principle that effects must follow their causes. The universe would require entirely new mechanisms to prevent logical paradoxes from arising, or it might exist in a state of constant logical contradiction that defies rational understanding. Consider a simple thought experiment involving two observers moving relative to each other at high velocity in a universe with infinite light speed. Observer A sends an instantaneous signal to observer B, who immediately responds with another instantaneous signal back to observer A. In our current universe with finite light speed, the relativity of simultaneity ensures that these signals maintain proper causal ordering regardless of the observer's relative motion. Each observer sees the signal exchange occurring in the logical sequence where the first signal is sent before the response is received. With infinite signal speed, the relativity of simultaneity disappears because there is no finite propagation time to create the time ordering effects that depend on relative motion. However, this could create situations where the response signal appears to be sent before the original signal is transmitted, violating the causal relationship between the two events. The universe would need new physical principles to prevent such paradoxical situations from occurring. Or it might exist in a state where logical contradictions are somehow permitted or resolved through unknown mechanisms. The implications for time travel and temporal paradoxes would be profound and potentially devastating for the logical consistency of physical law. In our current universe, faster than light travel or communication is impossible, which provides a natural protection against grandfather paradox type situations. Even theoretical concepts like traversable wormholes or exotic matter with negative energy density face severe constraints from causal protection theorems that prevent paradox formation. With infinite light speed, these protections would disappear entirely. Information could potentially flow backward in time through complex chains of instantaneous communication, creating closed time-like curves where effects precede their causes. A signal sent from Earth could theoretically reach a distant location instantaneously, be processed and retransmitted through a series of relay stations, and arrive back at Earth before it was originally sent, carrying information about its own future transmission. Such causal loops would create fundamental logical contradictions that could destabilize the entire framework of physical law. The universe might require exotic new principles to resolve these paradoxes, perhaps through quantum mechanical effects that prevent information from propagating in ways that create temporal contradictions, or through modifications to the laws of logic themselves that allow contradictory statements to be simultaneously true. The concept of free will and determinism would face unprecedented challenges in a universe where effects can precede their causes. Currently, the assumption that the future is not yet determined relies partly on the fact that information about future events cannot travel backward in time to influence present decisions. If you knew with certainty what choices you would make tomorrow, the meaning of choice and free will become philosophically problematic. With infinite light speed potentially allowing information loops that carry future information into the past, the entire concept of an undetermined future could become meaningless. Decisions might be influenced by knowledge of their own future consequences, creating strange, recursive loops where choices are made based on information about the results of those very choices. The philosophical foundations of morality, responsibility, and human agency could require complete reconstruction in a universe where temporal paradoxes are possible. Quantum mechanics would face fundamental challenges in maintaining its probabilistic interpretation if information could flow backward in time. The quantum measurement process relies on the assumption that measurement outcomes are not predetermined, but rather emerge probabilistically when observations are made. This probabilistic nature is thought to be fundamental rather than resulting from incomplete knowledge about hidden variables. If information about quantum measurement outcomes could somehow travel backward in time through instantaneous communication channels, the entire probabilistic framework of quantum mechanics could collapse. Quantum systems might become deterministic rather than probabilistic, with measurement outcomes predetermined by future information flowing backward through time. The wave function collapse that occurs during quantum measurement might be influenced by knowledge of future measurement results, creating paradoxical situations where quantum states are determined by their own future evolution. The many worlds interpretation of quantum mechanics, which suggests that all possible measurement outcomes occur simultaneously in parallel universes, could face new complications if information can flow instantaneously between different parts of the multiverse. Currently, the different branches of the multiverse are thought to be causally isolated from each other, preventing information exchange between alternative histories. With infinite communication speed, it might become possible for information to flow between different branches of the multiverse, potentially allowing observers to receive messages from alternative versions of themselves in parallel universes. This could create paradoxical situations where people receive information about events that never occurred in their own timeline, or where decisions in one universe are influenced by knowledge of what happened in alternative universes where different choices were made. The principle of locality, which requires that objects are only directly influenced by their immediate surroundings, would be completely violated by instantaneous action at a distance. Currently, all known fundamental interactions propagate at finite speeds, ensuring that distant events cannot instantly affect local conditions. Electromagnetic forces propagate at light speed, gravitational effects travel as gravitational waves at light speed, and even the strong and weak nuclear forces have limited ranges that prevent instantaneous long-distance interactions. With infinite light speed, electromagnetic and gravitational effects could act instantaneously across arbitrary distances, potentially creating a universe where every part influences every other part simultaneously. This could lead to unstable feedback loops where small changes in one location instantly affect conditions everywhere else in the universe. which then instantly affects the original location, creating chaotic oscillations that prevent stable structures from forming or persisting. The conservation laws that govern physics, including conservation of energy, momentum, and electric charge, might become impossible to enforce in a universe with instantaneous information propagation. Currently, these conservation laws are intimately connected to symmetries in the laws of physics through Noether's theorem, and they depend on the finite speed of signal propagation to prevent violations from occurring. If energy or momentum could be transferred instantaneously across arbitrary distances, it might become possible to create systems that violate conservation laws by rapidly shuffling conserved quantities between distant locations faster than information about the transfers can propagate. With infinite propagation speed, such violations might become undetectable or lead to logical contradictions where the same energy appears to exist in multiple locations simultaneously. The second law of thermodynamics, which requires that entropy increases in isolated systems over time, could face fundamental challenges if information can flow backward in time. This law provides the thermodynamic arrow of time that distinguishes past from future and explains why certain processes are irreversible. Heat flows from hot objects to cold objects, gases expand to fill available space, and organized systems tend to become disorganized over time. If information about future states could influence past conditions through backward time communication, it might become possible to create systems that violate the second law of thermodynamics. Knowledge of future entropy states could potentially be used to organize systems in ways that decrease rather than increase entropy, creating machines that spontaneously extract useful work from thermal reservoirs without any external energy input. The entire framework of scientific methodology relies on the assumption that experiments conducted under identical conditions will produce identical results, allowing for reproducible observations that form the foundation of scientific knowledge. This reproducibility depends partly on the causal isolation of experimental systems from external influences, particularly influences from the future results of the experiments themselves. With infinite light speed potentially allowing future experimental results to influence past experimental conditions through complex information loops, the reproducibility of scientific observations could become impossible to guarantee. Experiments might produce different results, depending on whether their future outcomes are somehow known or unknown, creating a form of temporal contamination that prevents objective scientific observation. Perhaps most fundamentally, the logical structure of mathematics itself could face challenges if physical reality permits contradictory statements to be simultaneously true. Mathematics relies on the principle of non-contradiction, which states that a statement and its negation cannot both be true at the same time. This principle underlies all logical reasoning and mathematical proof. If temporal paradoxes create situations where contradictory statements about physical events are simultaneously true, the mathematical framework that describes physical reality might require reconstruction using non-classical logics that permit contradictions. Such alternative logical systems exist in mathematics, but they are far more complex and counterintuitive than classical logic, and their application to physical reality would represent a revolutionary departure from thousands of years of rational thought. The universe might develop exotic new mechanisms to resolve these paradoxes and maintain logical consistency, perhaps through quantum mechanical effects that prevent paradoxical information loops from forming, or through modifications to the structure of space-time itself that preserve causal ordering despite infinite signal speeds. Alternatively, we might discover that logical contradictions are somehow permitted or resolved through principles that transcend our current understanding of reason and rationality. The elimination of finite light speed would force humanity to confront fundamental questions about the nature of logic, causality, and rational thought itself. The universe might remain logically consistent through mechanisms we cannot currently imagine, Or it might exist in a state of perpetual logical contradiction that challenges our most basic assumptions about the nature of reality and the possibility of rational understanding. The speed of light is far more than just another number in the vast catalogue of physical constants that describe our universe. It represents the fundamental architecture of reality itself, the cosmic speed limit that weaves together space and time into a coherent tapestry where cause and effect maintain their logical relationship, where the past remains fixed and the future stays open to possibility, and where the rich complexity of cosmic evolution can unfold over billions of years of cosmic history. Make this speed infinite, and our universe becomes utterly unrecognizable, transformed into something that would be simultaneously simpler in some ways, yet infinitely more strange and chaotic in others. Without the finite speed of light, we would lose the profound depth and historical perspective that makes cosmic exploration so magnificent and meaningful. The night sky would no longer be a time machine that allows us to peer billions of years into the past, witnessing the birth of the first stars, the formation of early galaxies, and the gradual assembly of cosmic structure over eons of cosmic time. Instead, we would see only a single instantaneous snapshot of the universe as it exists right now, stripped of the epic narrative of cosmic evolution that has captivated human imagination and driven scientific discovery for generations. The elegant mathematical framework of relativity, which has guided physics for over a century and enabled technologies from GPS navigation to nuclear power, would crumble entirely. Time dilation and length contraction, the strange but beautiful effects that reveal the deep connection between space and time would vanish completely. The profound insight that mass and energy are equivalent manifestations of a single underlying reality would lose its mathematical foundation. The geometric interpretation of gravity as the curvature of space-time would become meaningless, forcing us to understand gravitational attraction through entirely different principles that we can barely imagine. Physics would fragment back into separate, disconnected theories for mechanics, electromagnetism, thermodynamics, and other phenomena, losing the unifying vision that reveals the deep connections between seemingly disparate aspects of reality. The standard model of particle physics, quantum field theory, and our understanding of the fundamental forces would require complete reconstruction from first principles. The entire intellectual edifice of modern physics, built up through centuries of careful observation and brilliant theoretical insight, would collapse like a house of cards. Technology and communication would undergo revolutionary changes, but at the cost of losing the very mechanisms that make precise measurement and scientific observation possible. Interstellar communication would become instantaneous, allowing real-time conversations with alien civilizations anywhere in the galaxy. Yet we would simultaneously lose the ability to study cosmic history and understand how the universe has evolved to its present state. Space exploration would gain unprecedented capabilities for real-time control and communication with distant missions, but navigation and positioning would require entirely new techniques that might not achieve the precision we currently take for granted. The logical consistency of reality itself would face existential threats from temporal paradoxes and causal violations that could unravel the rational foundation upon which all scientific understanding depends. Information flowing backward in time could create grandfather paradox situations where effects precede their causes, forcing us to either discover exotic new principles that preserve logical consistency or accept a universe where contradictory statements can be simultaneously true. The very possibility of rational thought and scientific methodology could be called into question in a cosmos where the future can influence the past. Perhaps most importantly, we would lose the cosmic perspective that reveals our place in the vast evolutionary narrative of the universe. The knowledge that we are made of elements forged in the nuclear furnaces of ancient stars, that our planet formed from the debris of stellar explosions that occurred billions of years ago, and that the atoms in our bodies have participated in cosmic processes spanning the entire history of the universe, depends entirely on our ability to observe cosmic history through the finite speed of light. Without this temporal window into the past, we would be cut off from understanding our own cosmic heritage. The speed of light limit is not a barrier that constrains our exploration of the universe, but rather the fundamental principle that makes the universe coherent, comprehensible, and rich with meaning. It creates the causal structure that prevents logical paradoxes, enables the formation of stable cosmic structures from atoms to galaxies, allows for the gradual evolution of complexity over cosmic time, and provides the observational foundation for understanding how reality operates at its deepest levels. In a universe with infinite light speed, we might gain the ability to communicate instantly across cosmic distances and observe astronomical events in real time throughout the cosmos, but we would sacrifice the historical depth that reveals how we came to exist in the first place. We would trade the profound story of cosmic evolution for a chaotic snapshot of an incomprehensible present, losing the very perspective that allows us to understand our place in the grand scheme of existence. The finite speed of light is not a cosmic speed limit that restricts our capabilities, but rather the organizing principle that makes organized, rational, evolved reality possible. It is the thread that weaves space and time together into space-time, the mechanism that preserves causality and prevents paradoxes, the foundation that supports the mathematical elegance of modern physics, and the window through which we can observe the magnificent story of how simple hydrogen and helium in the early universe gradually evolved into the rich tapestry of stars, planets, galaxies, and ultimately conscious beings capable of contemplating their own existence. Without this fundamental constant, the universe would not be the cosmos we know and love, filled with history, mystery, and the possibility of gradual understanding through patient observation and careful thought. It would be something alien and incomprehensible, perhaps simpler in its lack of relativistic effects, but infinitely poorer in its absence of temporal depth and evolutionary context. The speed of light does not limit our potential. It defines the very nature of reality itself, creating the conditions under which complexity, consciousness, and cosmic wonder can emerge and flourish across the vast expanse of space and time.